What if I told you that a huge chunk of the internet, everything from sending an email to how your bank keeps your money safe, is all based on one single powerful idea? And that idea comes from a research paper from 1984. It's not about faster cables or some crazy complex code. Nope, it's about a fundamental shift in how we think about building reliable stuff. So let's dive into this core principle that's quietly running our digital world.
It all kicks off with what sounds like a really simple question. Imagine you need to send a file from your computer to a friend's computer, and it has to get there perfectly. I mean, 100% intact. No mistakes, no weird glitches, nothing. How can you be absolutely, positively sure it worked?
Okay, so on the surface, the process seems pretty straightforward, right? You've got 3 basic steps. 1. Read the file from the first disk. 2. Send it across the network. 3. Write it onto the second disk. I mean, what could possibly go wrong?
And our first instinct, our logical gut reaction, is just as simple. We think, okay, let's just perfect every single link in that chain. We'll build a super reliable disk reader, a flawless network, and a perfect disk writer. Because if every single piece is perfect, then the whole system has to be perfect, doesn't it? Well, this is exactly where our intuition leads us down the wrong path.
So, Section 1, a perfectly flawed system. To really see why this whole perfect links in a chain idea falls apart, we've got to look at a real-world example from MIT, where a tiny, almost invisible bug caused some truly catastrophic failures.
The authors of the paper point to this real-life problem at MIT. There was this network gateway, a box that connects different networks, and it had this tiny intermittent bug. Just once in about every million bytes it processed, it would accidentally swap 2 bytes of data. It sounds so small, almost insignificant, but the consequences, they were huge.
Now here's the wild part. The network itself was designed to be reliable. It had all sorts of checks and balances between the different machines. But here's the catch. The error wasn't happening between the machines on the wire. It was happening inside one of them, in that split second where the data was supposed to be safe, just sitting in memory. All that protection was in the completely wrong places.
So the result of this tiny little bug was this slow-motion disaster. Over time, really important operating system files were being sent through this gateway and just silently getting corrupted. And the only way anyone ever figured it out was when their system started acting weird, and they had to fall back on the ultimate end-to-end check, a human being, manually comparing the bad files on screen to old paper printouts. The human had to be the last line of defense.
This whole mess sets the stage perfectly for the solution. So, Section 2, the end-to-end argument. This is the principle that explains not only why that MIT system failed, but gives us a completely different way of thinking about how to build things that actually work.
So the central idea is this. The only place you can truly 100% guarantee a successful file transfer is at the very beginning and the very end of the journey, in the application itself. Why? Because the application is the only thing that actually knows what the file is supposed to look like. To the network in the middle, it's all just a random stream of ones and zeros, so any checks the network does are by definition incomplete.
Just think about it this way. The network, it only sees little pieces of the trip, the hops between computers. It has no idea if the file was read off the disk correctly in the first place, and it has no idea if it'll be written to the new disk correctly at the end. But the application sees the entire journey from start to finish. It can create a special signature, a checksum, of the original file, send it, and then have the application on the other end do the same check. Only a perfect match gives you a real guarantee.
So you might be thinking, does this mean all those checks inside the network are totally useless? And the answer is, no, not at all. Which brings us to Section 3, helpful but not essential. Their job is just different than what we might think. They aren't there for correctness, they're there for something else entirely. It really all boils down to performance. Okay, imagine you're sending a giant file over a really bad, spotty Wi-Fi connection. Your end-to-end check might keep failing, forcing your application to start the whole transfer over and over and over again, maybe 100 times. But on a more reliable network, one that has its own checks in the middle, that final end-to-end check might only fail once, or maybe not at all. You still absolutely need that final check, but you don't have to use it nearly as often. And that is the key takeaway, right there. The network's job isn't to guarantee correctness. Only the application at the ends can do that. The network's job is simply to be a performance optimization. It's there to make the path smoother and make failures happen less often so the application doesn't have to waste its time constantly fixing problems.
All right, section 4. It's not just about files. Because once this idea clicks, you start seeing it everywhere. It applies to so much more than just moving data around.
For example, think about a delivery guarantee. The network can promise it delivered a message to a machine, but it has no way of knowing if the application on that machine actually opened it or did anything with it. For that, you need an end-to-end confirmation. Or how about data encryption? Sure, the network can encrypt the data while it's in transit, but that data is sitting there, totally exposed inside the computers at both ends. For real security, you need end-to-end encryption handled by the apps themselves. You see the pattern? It just repeats over and over again.
And that brings us to our last section. This isn't just some niche rule for computer networks. It's a really fundamental principle for designing almost any kind of complex system you can imagine.
The original paper even points out how this thinking is baked right into the design of modern computer chips in something called risk architecture. It's the whole reason banking systems have these big high-level audits to catch the errors that slip past all the day-to-day checks. It's even why an airline agent will verbally confirm your reservation with you. They are the end-to-end check, because deep down they can't fully trust every single computer system between you and your flight to be perfect.
Ultimately, what the end-to-end argument does is push the complexity to the edges of a system. It argues for a simple, kind of dumb core and really smart, capable endpoints. And this forces us to ask a really fundamental question, not just about our software, but about any system we build. Where should the responsibility truly lie? Should it be with the complicated hidden machinery in the middle, or with the intelligent applications, and maybe even the people at the very ends?